Hello students, this is Lalit Yadav. I hope you all are fine in your home. Today I am going to deliver a lecture on the reliability. Reliability of a system, equipment or the product is very important aspects of the quality for its consistent performance over its expected life span. In fact, uninterrupted services and the hazard-free operation like the electrical generator, communication network, automobile, etc. In the simplest sense, the reliability means how long an item such as any machine, device, equipment will perform its proposed function without a breakdown. These are the definitions of the reliability. First, the reliability is the probability of a device performing its purpose adequately for the period of the time intended under the operating condition encountered. The second definition is the reliability of a system or device is the probability that it will give the satisfactory performance for a specific period of the time under specified condition. The third definition is the probability of no failure throughout the prescribed operating period. The other definition is the ability of the product to perform as expected over the certain period of the time. Now, these are the some important definitions used in the reliability. First is the probability. Probability is a value between the 0 and 1. This is a numerical value which is between the 0 and 1. The number of times that an event occurs successfully divided by the total number of trials. So for example, the probability of 0.91 means that 91 of the 100 items will still be working as the stated time under the state conditions. Second definition is the performance. Some criteria to the define when how product fail, which also describe what is the considered to be the satisfactory system operation. Third definition is the operating condition. This describes the operating conditions, that is the environmental factors, humidity, vibrations, shock, temperature cycle, operational profile, etc. that corresponding to the state product of the life. For, for the uh, successfully and the satisfactory operation of any system, the performance and the operating conditions and the probabilities are required. Now the basic elements of the reliability, it requires or the adequate specification. So these are numerical value of the probability, statement defining successfully product performance, third, statement defining the environment in which the equipment must operate. Fourth, statement of the required operating time. Next, the type of distribution likely to be the encountered in the reliability measurement. The reliability follows the distribution of the Poissons. So this is the representation of the reliability, the exponential of the or e raised to the power minus capital T upon theta. So theta is the mean life and capital T is the required life. On the same, in the some of the products, the best operating conditions are the given in the instructions manuals, so that can be followed for the reliability. Now the next is the uh, bathtub curve, which shows the failure rate over the life of the products. The failure rate is the expected to vary over the life of the products. So this is for the complex products offered often follows a familiar patterns of the failure. When the failures rate means number of failures per unit time is the plotted against the continuous time scale. So this curve exhibit and the distinct zone. So as you see in the curve, so on the y-axis we take the failure rate, and on the x-axis we take the time, and this is the curve. It is divided into the three zones. The first zone is the earlier failure period, second is normal operating period, and the third zone is wear out period. So curve from A to B is the also called the infant mortality. So this is the characteristics by the high failure. It begins at the first point during the manufacturing period. The curve B to C shows as you use the product which have the constant life in this time period, it is the work successfully or little bit chance of the failure. In this period, the chance of the failure is constant from B to D. And the curve C to D, it shows in this period the chance of the failure is increasing due to the wear of the part, due to the corrosion, wear out, friction, etc. So this is the details about the curve A to B. It is also called the earlier failure, infant mortality, deburring, or the breaking. So it is the different names. It may be the teething problem, the caused by the design, material blocks. So these are the reason behind the earlier failures. For example, the joints are not properly uh, jointed, and the weldings are not properly done, contamination due to the atmospheric gases, misuse of the products, misassembly of the products. And B2C is also, this line shows the specific failure rate, and this shows the constant failure, or the it is very important zone of the useful life of the product. So lower than the initial failure rate and more, or the constant until the end of the life. The C to D is the end of the life wear out phase. The failure rate rise against due to the component reaching end of the life. For example, the corrosion, cracking, wear, friction, fatigue, erosion, etc. Now the achievements of the reliability. So these are the factors on which the achievements of the reliability depend: design, production, measurement and testing, maintenance, field operation. So the design is the very important aspect of the reliability. So there are the five effective areas of the achievement as we see in the previous slides. So these are the five effective areas of the achievements of the reliability. So one of the important factor is the design. So designing of the reliability. So these are the important factors for the designing of the product. Simplicity of the product. So design should be simple. So design of the products are as simple as possible, and the error rate is directly proportional to the complexity. Second is the derating, providing the large safety margin. For example, a table bears the 100 to 150 kilogram of the load, but actually we use the 10 to 50 kilogram of the load on it. So any of the product we can take the factor of safety. Redundancy, uh, provision of standby or the extra assembly are the available. The extra assembly items are the provided in the product. For example, stepney is provided in the vehicles, extra fuse is provided for the battery of the car. Safety operations. If any part is failed, the safety keeps in the mind. If the possible if possible failure should occur in non uh, non-catastrophic manner and no harm to the operator. For example, the safety valve is provided in the cooker. Next is the protection from the extreme environment condition, and items provide in the design for the protection. For example, the shock absorber is provided in the any machines or the device. And next is the maintainability and the serviceability. So any of the products are easily be maintained and easily be serviceable. Now the next slide is of the measurement of the reliability. So this is the basic measurement of the reliability of the products. So the probability of the survival of that of the MTBF means mean time between failure. Let small n is equals to the sample of the product from the large size. NT is the number of items failed in time period T. The probability of the failure in the time period T is represented by this Tt. So the performance, the total performance in time T we take here. So this is the probability of the failure of the in time period T. So it is Nt upon N. So for the performance for the total time period, so summation Nt upon N, and the reliability can be calculated by this. So 1 minus probability of the failure. So this is the value of probability of the failure. So reliability can be calculated 1 minus probability of the failure. So it can be written the RT is equals to 1 minus summation NT upon M. When the large number of products for the it is represented with the function ft, so it can be written like that. So rt is equal to 1 minus integrate 0 to t and ft dt. So ft is the function that is equal to the 1 upon theta e raised to the power minus small t upon theta. So here the theta is stand for the mean life or mean time between the uh, mean time between failure. Therefore, this equation can be put the value of ft here. So this equation can be written in this form: rt is equals to 1 minus integrate 0 to t 1 upon theta e raised to the power minus small t upon theta dt. So after the integration, we obtain this value rt is equals to e raised to the power minus capital T upon theta. So capital T denotes the required life of the products. The failure rate is represented by the lambda and can be shown in case to be the reciprocal of the mean time to the failure. So it can be written in this form: lambda is equals to 1 upon theta. So here we replace the 1 upon theta is replaced by the lambda. Therefore, the expression of the reliability becomes RT is equals to e raised to the power minus lambda t. Now the next slide is of the cost of the reliability. So in this curve, on the y-axis we take the cost of the reliability, and on the x-axis we take the reliability. So this curve shows the unit investment of the reliability. So when the reliability value is less, then the cost will be also less. And if we require the more reliability of the product, so the investment on the reliability will be increased. So the cost will be increased of the reliability. Okay. Now this curve shows the unit cost of the failure. If the reliability increase, the unit cost of the failure will be decreased. And this curve shows the total cost per unit. So this is the resultant curve of both the curves. So if the specified reliability is much lower than the optimum, the actual cost of the customer may be high due to the excessive repairs and the maintenance. Now the maintainability, these are some other important terms which is also used in the reliability, that is the maintainability, a characteristics of the design, installation and operations usually expressed as the probability that the item can be retained in or restored to specified operable conditions within a specified interval of the time when the maintenance is performed in the accordance with prescribed procedures. So the maintenance action is the prescribed operations to the correct and equipment failures. Second definition is the availability, a measure of the time that a system is actually operating versus the time that the system was planned to operate. So it is the probability that the system is operational at the random time t. So mathematically, you can find out the or measure the inherent or the potential availability by this formula mu upon lambda plus mu. So or it is also written like that, MTBF, mean time between failure, upon mean time to repair plus mean time between failure. So lambda is the mean time. So what is the meaning of lambda? Lambda is the failure rate and it can be calculated by 1 upon MTBF, and mu is the repair rate and it can be written is equals to the 1 upon MTTR. MTTR means mean time to repair. Now the next term is the failure rate. So the number of failures per unit of the gross operating period in terms of time, event, cycle, etc. MTBF means mean time between failures. So the average time between the failure occurrences, the number of items and their operating time divided by the total number of failures for repairable items. So mathematically we can write the mean time between failure is equals to 1 upon lambda, or total test time upon the number of failure during the test. Now the next term is mean time to failure, MTTF. The average time to failure occurrences, the number of items and their operating time divided by the total number of the failures to the repairable item or the non-repairable item. So MTTR can be written mathematically the total maintenance downtime upon the total number of maintenance time. Now the next term is maintenance action rate. It is represented by the mu. So maintenance is the numeric value representing the number of maintenance action carried out in the particular time. So mu is equals to 1 upon MTTR. Mathematically we write in this form, MTTR is equals to summation of Ni lambda I Tmi upon uh, summation Ni lambda I. Ni is the number of the similar parts and lambda I is again the failure rate, or Tmi is the predicted maintenance action time. Now here you can see this is the series configuration. If the systems are the arranged in the series like A, B and C up to the N system. So these are the arranged in the form of series. And in the second, here you can see it is arranged in the form of parallel configuration. So that is A, B and C. So these are arranged in the parallel form. So when the system is in series configuration, then you can use this formula for the reliability RS for the time t. So R1t into R2t into R3t into R4t and so on. And if the system is in parallel, then you can use the formula for the parallel redundancy. So RT RS T is equals to 1 minus uh, 1 minus R1. So these are the numerical problems. So first numerical is based on the series system. So the numerical problem is the following reliability requirement has been set on the subsystems of the communication system. The subsystems are the receivers, control system, power supply, antenna, and the reliability of a 4-hour period, that is the receiver reliability is 0.970, control system reliability is 0.989, and the power supply system reliability is 0.995, and the antenna reliability is 0.996. So what is the expected reliability of overall system? So as we know, these systems are the arranged in the form of series. So we use the formula of the series system RS T is equals to R1T into R2T into R3T into R3 R4T. So this is the reliability values. So directly the R1T, R2T, these values are the given in the numerical. So we put all the values here, and the total reliability of the series system is the 0.95, or it is in percentage 95 percentage. Therefore the chance that the overall system will be perform its function without failure for a 4-hour period is 95%. The second numerical problem is based on the parallel redundancy. So numerical is a unit has a reliability of 0.99 for a specified mission time. If two identical units are used in parallel redundancy, what overall reliability will be obtained? The solution, when the parallel redundancy is used, so we use this formula RST is equals to 1 minus RT raised to the power n. RST is the reliability of the system, we know, and R1 is the reliability of the individual elements of the redundancy, and n is the number of identical redundancy elements. So RT1 value is given here 0.99. We put this value here in the formula in place of R1, and the this is n is equals to 2 for the two identical units. So n is equals to 2. So we put the value of 2, n where n is equals to 2, and then we calculate this value. So the reliability of the parallel redundancy is 0.999, means 99.9 percentage. So this is the lectures on the reliability. If you have any problem, then you mail me or you may call me. Thank you.